Now in section 14.6 we have a slightly unusual situation. I'm going to show you all the methods that are in examples 14, 15 and 16, but I just want to put a note in here. Example 14 and 15 are important, and this is perhaps the way that you might think of doing it. If you've never met logarithms before, what they do in example 14 seems to be the most sensible thing to do, and it works perfectly well. Example 15 is really worth noting because this comes up in exams and people forget it, and it costs a lot of marks. It's not particularly difficult, but it costs a lot of marks. But mostly when you deal with logarithms, it's example 16 is the method that we're going to use. We'll hardly ever use example 14 and 15, and we'll hardly ever use the method in example 14. We will use these ones when they come up on exams. But example 16, pretty much every single time you meet an equation where the unknown is up there in the index, this is the method you're going to use. And just be aware of that as we're doing this chapter, that 14 is a perfectly good method for this particular exercise, but after this, go straight for this method, example 16, on pretty much every occasion. And if you want to start using it straight away in exercise 14, then that's fine. So let's have a look. 3 to the power of x equals 20. All of these equations have the exponent, the index, is where the x is. Okay, where the unknown is, it's in the index. So how do I undo that? Well, just do the same thing on both sides of the equation, right? Standard balance method. What's the opposite? What's the inverse function here? And because the x is in the exponent, the inverse function is logs. So log base 3 of 3 to the power of x is going to give us an x on the left-hand side. If I've done log base 3 on the left-hand side, I do log base 3 on the right-hand side. And then I type log base 3 of 20 into the calculator, and it comes out as about 2.727. Okay, so that's straightforward. And the same thing happens with part B, only in this case we take log base 5 of both sides. And, well, it's probably quicker to write it out than trying to save time not doing. 4x minus 1 equals 61. If I take log base 5 of this side, I end up with 4x minus 1. If I take log base 5 of this side, I get log base 5 of 61. So x equals log base 5 of 61, add that 1, divide by that 4, stick that in the calculator, and out comes the answer. So far so good, okay? Now, here's another thing we could have done, and at this point this is going to seem odd, but when we look at example 16 it'll seem less odd. Remember, log, where I don't write a base, means log base 10, okay? Well, I'm going to write... I'm going to take this one here, 3 to the power of x equals 20, and I'm going to take logs on both sides, but I'm just going to take log base 10. Well, now, this x, by the index rule, can come down to the front. So in a couple of lines of algebra instead of one, I've got to this stage, and now I've got to stick it in the calculator, okay? Now, why is that a more useful method? Well, if we flip now to example 16, what if I've got an equation like this? 3 to the power of x equals 2 to the power of x plus 1. And you could think, well, if I took log base 3, then this I'd get rid of this 3 to the power of x and I'd just have an x. But then if I take log base 3 of 2 to the power of x minus 1, I've got a bit of a problem, right? I've not got rid of it. I can't take log base 2 because I'd get rid of the 2 and the x plus 1 would come down, but then not over this side. If I just take log base 10, or in fact log of any base, it doesn't have to be 10, it's just 10 and e are the standard logs. In fact, after this, I'm using log base 10 at this point because the book does. What we'd normally do would be take log base e, which is natural log. So, well, let's do both. It looks exactly the same, apart from when you type it in the calculator. So let's do natural log of 3 to the power of x equals natural log of 2 to the power of x. And remember, ln stands for natural log, which is log base e. So now we use the power rule. And over here it would look the same. X natural log of 3 equals x plus 1. Sorry, forgot the plus ones. Natural log of 2. Now at this point, look, I've got x log 3 on this side. On this side I've got x log 2 plus log 2. So if I take this over this side, I get x log 3 minus x log 2 equals log 2. And then there's my answer. Okay, and I've got to stick that lot in a calculator. The trick is, all the methods, we've got to get the x out of the exponent. If you pick the base of your logarithm up here, sometimes there's a shortcut. But rather than saying, well, I've got to think about the base and all sorts of different nasty algebra is going to come up and then I'm going to have to stop and work out what's the best base to take, let's just always take log base 10 and we can bring the exponent down using the power rule, okay? In fact, we're not even going to bother with log base 10, we're going to take natural logs in pure maths almost all the time, and I'm not going to bother keeping writing this out because it'll look exactly the same, only everywhere I've written log, just replace it with an ln. Obviously, I'd then have to type in a different button on the calculator, right? But it's still going to give me the same answer. Natural logs tend to be the ones that we use more in maths. Logs base 10 tend to be used a bit more in science and engineering or applied maths. There's no mathematical reason why one is any different to the other for this particular example, okay? But natural logs tend to come in handy a bit more in pure maths kind of ways. I won't go into that too much, but they just sort of seem to fit a bit better. I suppose there's an argument for saying it really doesn't matter. We could use any base for this technique, and we could use any base in a lot of other situations, but natural logs, I suppose, then are just the ones that mathematicians seem to prefer. I suppose the other practical advantage seems silly, but you know, we only have to write 2 figures instead of 3. We don't have to write log, we just have to write ln. We just save a little bit of ink and effort. So there we go. So that's the method for example 16. That's the method that I suggest you use whenever you can, right? Just take logs on both sides, log base 10 if you like it, log base e if you prefer that, and then all the exponents come down through the power rule, and we should be able to solve from there. Now, example 15, I'm going back to this one, and if you look, there's question 2 here. Now, this is really, really worth noting, putting some sort of highlighted point in your folder, because these questions come up every now and then, and when they do, they cost a lot of people a lot of marks, not because they're hard, but because we haven't seen them for a while. They're one odd little corner of the book, and we lose marks. In a lot of ways, the exam is a test of how well do you know this textbook. And when this comes up, the people that know this textbook really, really well remember this exercise and can do these questions. And the people that don't know the textbook quite as well lose the marks because they've missed this little corner of it. So, the way to see this one is if you look at it, it looks like a quadratic. Now, they're being nice there, right? This is an example. It's not always going to look so obviously in the shape of a quadratic. Here, look, I've got 3 terms and an equals 0. So I'm feeling sort of quadratic-y already, and maybe that's our hint. If I take that hint, well, this is 5 to the power of x all squared, isn't it? By the power rule for indices. So if I now say, okay, let's let y equal 5 to the power of x, this is y squared minus 12y plus 20. So y, if I factorise here, and I can do it with a 10 and a 2, I think, so minus 10, minus 2, there we go. So y equals 10 or y equals 2 are my 2 answers. But it wasn't a y, it was a 5 to the power of x. So what I've got here is 5 to the power of x equals 10, or 5 to the power of x equals 2. Okay? Now I've got a simple logarithmic equation that I can solve. The tricky bit here is this. So let's just finish solving these. Just natural log of 5 to the power of x equals natural log of 10. And I'm using the method that I recommend that we go for, even though there is a slightly quicker way. So that's x equals natural log of 10 over natural log of 5, and stick that in the calculator. And then similarly here, we're going to get x equals natural log of 2 divided by natural log of 5, and I'm sure you can join the dots to get to there if you need to just follow exactly these steps, but with a 2 instead of a 10. So the tricky bit is this. You wouldn't spot that for yourself necessarily, and it doesn't matter because you don't need to spot it for yourself. You've been shown it now. So if you revise carefully and remember to revise this bit, then when they give you one of these or anything that looks like one of the questions out of question 2, you go, that's one of those ones where I need to make it look like a quadratic. So I'll just quickly do 2e. If they're being horrible, it'll look like this: 7 to the power of 2x plus 12 equals 7 to the power of x plus 1. So if you see that on an exam, you're going to look at it and it doesn't look like a quadratic. It's not everything over one side equals 0. It's not 3 terms equal to 0. It looks very like, we should solve this with logs. But the only way we can solve it with logs is through this same method. So 7 to the power of 2x, take away 7 to the power of x plus 1, plus 12 equals 0. So that is 7 to the power of x squared. Now, this is 7 to the power of x plus 1. So that is 7 to the power of x times 7 to the power of 1, okay? So in other words, it's 7 lots of 7 to the power of x plus 12 equals 0. So this is, if I now let y equal 7 to the power of x, I get y squared minus 7y plus 12 equals 0. I can solve for y. I can replace y again with 7 to the power of x, and then I can use my simple log equations technique, and we're done. Okay, that is section 14.6. I know I haven't, as I said at the start, I haven't covered every possible question they can ask you, but those are some of the examples, and from there and a bit of practice, I think hopefully you'll be able to put it all together. Good luck.